Appuswamy, an assistant professor at Eurecom, and I'm here to present our work on universal layout emulation. This work is done in collaboration with Vincent Joguin from EUPALIA. Driven by the promise of AI and data analytics, enterprises are routinely gathering vast amounts of data. However, not all data gathered is uniformly accessed. Nearly 80% of it is cold, meaning infrequently accessed, and this cold data is increasing at a 60% cumulative annual growth rate. Naturally, enterprises have put in place sophisticated storage tiering and archival infrastructure for archiving and preserving this cold data over long time periods. And the figure shows a typical infrastructure. In this infrastructure, data that needs to be archived is extracted from a DBMS into an archival file, which is then stored on tape, which is the lowest cost, highest density storage media we have available today. Later, when the data needs to be restored back, it's read from tape, the archival file is read from tape, and it's then loaded back into the DBMS. Unfortunately, the tape-based archival infrastructure described here has several fundamental limitations. First, a recent study from the Storage and Networking Industry Association reported that 60% of archival data is stored longer than 20 years. Unfortunately, the lifetime of all storage devices we have available today, including tape, is less than 20 years. Second, the annual density improvement in tape is about 30% per annum, which means that every few years the tape industry comes out with a new generation of tape. And unfortunately, the tape industry provides backwards compatibility only with two previous generations, as shown in the table in the bottom, where the LTO6 tape drive will not be able to read tape from LTO3, 2, or 1 generation 1. The net effect of these two issues is the fact that data stored on tape needs to be periodically migrated from one generation to another, and enterprises have to face the costs involved in this data migration. In addition to the media obsolescence issues we described earlier, the current archival infrastructure also suffers from format obsolescence issue. We know that DBMS store data in a compressed binary format. However, when we need to archive the data from the DBMS out of the DBMS, we need to store it in a format that's future compatible with all future DBMSs. As a result, we cannot assume anything about the on-disk layout of archival data. So the state of the art in archiving data converts data from the compressed binary format into a DBMS independent textual format where data is stored in CSV files and represented using XML or JSON tags, and this naturally leads to a massive data bloat. So the net effect of this architecture that we have today is the fact that the archival cost is growing dramatically due as enterprises are archiving more data due to the need to constantly migrate text-based bloated archival data. The motivation for this work came from decades of experience by museums and archives where they have used analog media like paper, microform, or film for preserving documents and artwork. Recent work has also shown that analog media can be used for preserving digital data by converting bits into visual barcodes like QR codes, and that can be printed on paper or shot to film. A good example of this is a recent work from the Norwegian company Pickle, which stored the UNICEF child rights documents, healthcare data, and several other types of data on silver halide cinema film. These analog media essentially solve the media decay and obsolescence problem because all these media have a lifetime of more than 500 years, and data stored and barcodes stored on paper or film can be retrieved using basic scanning technology. So there is no need to migrate data once it's stored on analog media. However, this analog media does not solve the data bloat caused by format obsolescence. In fact, they bring about new issues in format obsolescence because they introduce new media layouts. Recall that I mentioned that storing data on film requires converting data into barcodes, which means getting data back from film requires decoding barcodes into digital data. These decoders are quite complicated, as you can imagine, because they use image processing techniques and complex error correction codes to deal with errors that can be introduced by scanning. Remember that if we have to store data, archive data on analog media, we will be able to read the barcodes back. But unless we store the decoding logic itself, we will not be able to convert the barcodes back into digital data. So it's extremely important that we archive the decoding logic in addition to the data itself. And this is something that state of the art does not address. In fact, if we are able to somehow come up with a technique to archive the decoding logic to convert barcodes into digital data, we can also solve the data bloat problem directly. This is because we can actually now store data instead of in a textual format, we can store it in a compressed format using data-specific, type-specific compression algorithms without having to worry that we will not be able to read the binary file later because we can store the database decoder together with the media decoder and store both decoding logics together with the data. So then the central question is, how can a user run a decoder that we developed today 100 years into the future on a computing platform that might not even exist today, right? In order to solve this problem, we draw on ideas from digital preservation. Particularly, we build on emulation, which is a technology used to simulate one hardware environment using another. Emulation is used in digital preservation for getting old software to run on modern computing environments. And we have also used emulation for running games from Sega and other gaming consoles on modern PCs. A subclass of emulation is what's referred to as universal emulation, and it's based on the observation that often we only need to preserve application logic and not the entire hardware or software stack. So if only we need to preserve the application logic, there is no need for us to emulate a complex processor like an x86 processor. Instead, we can build a virtual processor, a processor that does not exist, which has a very simple ISA, with the goal that building an emulator for this virtual processor is very easy because of the simplified ISA. And we can rewrite our software to target this virtual ISA. This technique is called universal emulation, and the central idea in this work is to use universal emulation to archive both the media layout decoder, which is used for converting barcodes into binary data, and the database layout decoder, which can be used for converting compressed data into uncompressed data together with the data. MicroLunus is the system that we developed in order to implement ULE, and I'm going to present a simple overview of the internal components here, and more details are in the paper. The first component is dbcoder, which is responsible for converting a textual data that you get from the database into a LZMA compressed binary stream. The second component, MOcoder, takes the binary stream from the dbcoder and converts it into barcodes. So together, the dbcoder and the MOcoder are responsible for converting textual archival dumps into compressed visual barcodes. The third and important component is Olonus emulator that emulates a simple but complete 23 set instruction set architecture we refer to as DynaRISC. So it emulates a software processor that provides 23 instructions. Okay? And using these components, MicroOlonus implements universal emulation by implementing the decoding parts of dbcoder. Remember, the decoding part of dbcoder converts compressed data into uncompressed data, and the decoding part of MOcoder converts barcodes into digital data, into compressed data. Okay, so we implement the decoding parts using these 23 instructions, the DynaRISC instructions. And once we have implemented this, the instructions themselves can be stored as plain text together with the data. So that's the central idea of MicroLunus. So here is an overview of how we would use MicroLunus for archiving data. As before, we extract the data in a textual format from the DBMS. Then instead of storing the textual file, we pass it to MicroLunus, which converts it into a series of emblems, which are our barcodes and some text. You can then go ahead and print these on paper or shoot these on film, and I'm showing you an example of a film that was generated using this approach. Later, when you need to recover the data back, you scan the film to get the barcodes as images, and using the text actually is a pseudocode description of a basic bootstrap emulator. So it's 3 pages of English description that you can use to implement a bootstrap emulator in any language of your choice on any computing platform of your choice. So the user will implement a bootstrap emulator. The emulator will automatically take as input the emblems, the barcodes, and you load the decoding algorithms that are necessary and automatically convert the barcodes into textual data that can be dumped into that can be loaded into a DBMS. Note here that all the user has to do is read 3 pages of English pseudocode and implement a basic bootstrap emulator that can actually convert the data automatically, right? And if you're interested in further details about the internal architecture, I refer you to the paper. A quick word about the experimental evaluation. We have used MicroLunus to archive 1 megabyte TPCH PostgreSQL database on paper. So we converted it into 26 pages of barcodes that we printed on an A4 paper, leading to about 50 kilobytes per page. So you have now paper being used as a digital storage media. We scanned back the pages as 600 DPI, and we implemented the bootstrap in C++ that automatically did the full decoding in 3 minutes on a Linux server. Similarly, we also stored a 102 kilobyte TIFF image by converting it into 3 pages of barcodes and printing it on microfilm and cinema film, and we successfully verified the end-to-end archival process and restoration process works. Further details, once again, are in the paper. To conclude, there are some fundamental issues in long-term archival infrastructure that we have today with tape. Particularly, we talked about media obsolescence due to the limited lifetime and compatibility of tape readers, and format obsolescence and the data bloat, particularly caused by our desire to avoid format obsolescence. Analog media like paper, microform, and film can solve the media decay problem, but they complicate format obsolescence. And in this work, we presented Microlinus, an end-to-end universal layout emulation system that enables cost-efficient compressed data archival using analog media. Thank you very much.